In the late 19th century, Europe was alive with the hum of discovery, invention, and change. The world was entering a new era, a time when the mysteries of electricity, magnetism, and the atom were beginning to attract the curiosity of some of the most brilliant minds humanity had ever produced. In the midst of this backdrop, in the city of Copenhagen, Denmark, a child was born who would one day become a cornerstone in this grand narrative of scientific progress. His name was Niels Henrik David Bohr. Niels Bohr entered the world on October 7, 1885, as the son of Christian Bohr and Ellen Adler Bohr. His family was not one of ordinary means nor of ordinary pursuits. Christian Bohr, his father, was a respected physiologist, renowned for his studies in the mechanics of the human body, particularly in understanding respiration and blood gases. He had been appointed a professor at the University of Copenhagen and was already recognized in European scientific circles. His mother, Ellen, came from a distinguished Jewish family of intellectuals and bankers. From the beginning, Niels Bohr was immersed in an environment where curiosity, intellect, and conversation were as natural as the air he breathed. Copenhagen itself was a city of charm and learning, a place where cultural and scientific ideas crossed paths. The Bohr household was often filled with discussions that spanned both science and philosophy. Guests at the dinner table included academics, artists, and thinkers, and the children of the family were encouraged to listen, absorb, and participate. Niels was not alone in this journey. He grew up with his siblings, among whom Harold Bohr would also go on to become famous in his own right, not in physics but in mathematics. Harold would eventually be recognized as one of the leading mathematicians of his era, and even represented Denmark as a football player in the Olympics. The Bohr family was, in essence, a household of brilliance and versatility. Niels, however, was a boy of quiet intensity. He was not the type to boast or to dominate conversation. Instead, he was contemplative, always thinking, always questioning. From an early age, he demonstrated a fascination with puzzles, with problem-solving, with finding order in what seemed at first chaotic. He was also known for a somewhat gentle and humble demeanor, a trait that would remain with him throughout his life and endear him to many of his colleagues later in his career. His father played a significant role in shaping the young boy's curiosity. Christian Bohr's laboratory was a place of fascination for Niels, who often watched experiments being conducted with instruments that seemed to him almost magical. There, he witnessed science not as abstract theory, but as living practice. The wearing of machines, the bubbling of glass beakers, and the meticulous recording of results all became part of the atmosphere he absorbed as a child. For Christian, science was not just a profession but a calling, and he instilled in his children the idea that knowledge was a pursuit of truth, one that required patience, discipline, and imagination. As Niels grew older, his schooling became a significant arena in which his talents began to surface. He attended Gammelholm Latin School in Copenhagen, where he proved himself a dedicated and gifted student. However, it was not mathematics or physics alone that shaped him at that time. The Danish education system emphasized languages, history, and philosophy as well, and Bohr absorbed these disciplines with the same quiet diligence he showed in his scientific studies. Unlike many of his peers who might have viewed the humanities as peripheral, Bohr was deeply influenced by them, and this influence can later be traced in the philosophical dimension of his scientific work. At school, Bohr was not considered a prodigy in the conventional sense. He did not always dazzle teachers with effortless answers or with extraordinary quickness. Instead, his strength lay in persistence, in depth of thought, in the way he returned again and again to a problem until it surrendered its solution. This methodical, almost stubborn approach became his hallmark. His classmates often remembered him as someone who thought long and deeply before speaking, but when he did speak, his words carried weight, for they were the product of careful consideration. The turning point in his academic journey came when he developed a deeper interest in physics, a subject that, at the dawn of the 20th century, was entering its own period of transformation. The discoveries of radioactivity by Henry Becquerel, the electron by J.J. Thomson, and the early works of Max Planck were already redefining the landscape of physics across Europe. To a young Niels Bohr, these were not just distant achievements of others, but glimpses into a realm of nature that demanded to be understood. When the time came for university, there was no hesitation in his choice. In 1903, Bohr enrolled at the University of Copenhagen, following in the academic footsteps of his father. At the university, he initially studied mathematics and philosophy alongside physics. He was particularly drawn to the works of philosophers such as Søren Kierkegaard, another son of Copenhagen, whose writings on paradox, uncertainty, and the limits of human understanding resonated deeply with him. Though physics would become his life's work, these philosophical underpinnings provided a unique lens through which Bohr later interpreted the meaning of quantum mechanics. At the University of Copenhagen, Bohr began to distinguish himself as more than a diligent student. He entered experimental physics with both enthusiasm and curiosity, often pushing beyond the limits of the equipment and resources available to him. In those early days, physics laboratories were not the high-tech research centers we imagine today. They were modest spaces, filled with fragile glass instruments, primitive electrical devices, and improvised setups. Yet it was in these laboratories that Bohr began to show his ingenuity. One of his first significant pieces of research involved the study of surface tension in liquids, a topic that may sound unassuming but required delicate experimental skill. The university had announced a competition sponsored by the Royal Danish Academy of Sciences, offering a gold medal for the best paper on the subject of surface tension. Niels Bohr took up the challenge. Using rudimentary equipment, much of which he fashioned himself, he designed experiments to measure the behavior of water jets and their relation to surface tension. It was a task requiring not only theoretical insight, but also meticulous hands-on precision. His brother Harold assisted him with the mathematical aspects, combining their respective strengths. The work was painstaking, but the results were groundbreaking enough to win him the gold medal. This recognition was more than just a student achievement. It was the first official acknowledgement that Niels Bohr had the potential to contribute meaningfully to the scientific world. The paper he wrote was later published, a rare feat for a young student at the time, and it immediately established him as a physicist with a promising future. From this point onward, Bohr's reputation began to grow, and so did his ambitions. He moved deeper into the study of theoretical physics, immersing himself in the works of Lord Kelvin, James Clerk Maxwell, and Ludwig Boltzmann. He wrestled with the complex equations that described thermodynamics, electromagnetism, and the behavior of matter. Yet, what set him apart from many of his contemporaries was his ability to blend theory with a philosophical awareness of the limits of knowledge. While others might see physics as a march toward certainty, Bohr increasingly viewed it as an exploration of what could and could not be known. During his student years, Bohr's relationship with his teachers was another defining feature of his education. He came under the mentorship of Professor Christian Christiansen, a leading figure in Danish physics. Christiansen recognized Bohr's talent but also his unusual style of thinking. Bohr was never satisfied with surface explanations. He probed deeper, sometimes even to the point of exasperating his instructors with endless questions. Yet Christiansen supported him, guiding his research and encouraging him to pursue physics as a lifelong vocation. By the time he completed his master's degree in 1909 and his doctorate in 1911, Niels Bohr had already shown signs of the brilliance that would later change the world. His doctoral dissertation, titled Studies on the Electron Theory of Metals, was highly technical and, in parts, criticized for being overly ambitious. However, it revealed Bohr's boldness, his willingness to tackle problems that even seasoned scientists considered intractable. He was unafraid to challenge established theories, and though not all of his arguments were correct, the very attempt marked him as a thinker of rare independence. The completion of his doctorate marked the end of the first stage of his journey, the early life and education of a boy from Copenhagen who grew up in a home filled with ideas, nurtured by a father who believed in science, shaped by a culture that valued philosophy and thought, and trained in the modest but fertile environment of the University of Copenhagen. This foundation would carry him forward into the wider scientific world, where he would soon encounter the likes of Ernest Rutherford and Max Planck, and where his name would become synonymous with the revolution of quantum theory. When Niels Bohr completed his doctorate in 1911, he stood at a crossroads that would determine the trajectory of his life and career. He had grown from the boy who tinkered with makeshift experiments in his father's laboratory to a young physicist whose bold ideas and experimental skills were beginning to attract attention. Yet, in many ways, his education was far from complete. The intellectual foundation laid in Copenhagen needed to be tested and expanded in the broader world of European physics, where the giants of the discipline were redefining the very language of science. His dissertation on the electron theory of metals had been both daring and controversial. It examined how electrons contributed to the physical properties of metals, but the theories of the time were not yet adequate to capture the subtleties of atomic structure. Though the work was not entirely successful, it demonstrated Bohr's courage in tackling unsolved problems and his ability to see beyond established frameworks. The University of Copenhagen awarded him his doctorate, and with it, he earned the right to step into the wider stage of international science. The early 20th century was a golden era for physics. Across Europe, laboratories in Cambridge, Manchester, Berlin, and Göttingen buzzed with discoveries. The electron had only recently been discovered, radioactivity was still a mystery, and the atom, once a philosophical idea, was becoming an object of experimental investigation. For a young physicist eager to explore the unknown, there could hardly have been a more exciting time. Bohr knew that to grow, he needed to learn from the leaders of the field. His first step beyond Denmark was Cambridge, where he arrived in 1911 to work under the famous J.J. Thomson, the discoverer of the electron and the head of the Cavendish Laboratory. Cambridge was a hub of experimental physics, brimming with the energy of discovery. For Bohr, however, the experience proved frustrating. He admired Thomson greatly, but he struggled to find common ground with his approach. Thomson was more cautious and less inclined toward the radical theoretical leaps that Bohr was beginning to imagine. The work he was assigned did not inspire him, and the intellectual connection he hoped for never fully materialized. Yet even in disappointment, Bohr learned. He discovered that not every great scientist would be a perfect mentor for him, and he realized that his own path might not lie solely in the footsteps of others, but in carving out new directions. His time in Cambridge was short, but it prepared him for the next, more fruitful chapter, Manchester. In 1912, Bohr moved to Manchester to work with Ernest Rutherford, the man who had recently astonished the world by proposing that atoms were mostly empty space, with a tiny dense nucleus at the center. Rutherford's laboratory was alive with the thrill of discovery, and unlike his time in Cambridge, Bohr immediately found himself in the right environment. Rutherford was energetic, bold, and open to fresh ideas, an ideal mentor for the imaginative young Dane. Here, Bohr witnessed firsthand the experimental breakthroughs that were reshaping physics. Rutherford's famous gold foil experiment had revealed the nucleus, challenging the long-standing plum pudding model of the atom. Bohr was fascinated. His own education in Copenhagen had given him the theoretical tools to analyze these discoveries, and his philosophical inclinations encouraged him to think about their deeper meaning. It was in Manchester that Bohr began to see the outlines of the ideas that would eventually lead to his revolutionary model of the atom. But before those groundbreaking achievements, there was still the matter of his personal growth. Bohr's early years abroad were also years of adjustment. He was a young man from a small country, entering the bustling scientific capitals of Europe. His modesty and quiet nature sometimes set him apart from the more boisterous personalities around him, yet his sincerity and intellectual depth quickly won respect. Even those who initially underestimated him soon recognized his rare ability to probe questions at their very core. At the same time, his ties to Copenhagen remained strong. In 1912, the same year he worked with Rutherford, Bohr married Margrethe N. Lund, who would become his lifelong companion and an essential support throughout his career. Margrethe was not a physicist, but she had a keen mind and a steady presence. She became his confidante, editor, and sounding board, helping him articulate complex ideas and grounding him during the pressures of his scientific life. Their partnership was one of quiet strength, and in many ways, it gave Bohr the stability he needed to pursue his demanding intellectual journey. When he returned to Denmark later that year, Bohr brought with him not only new scientific insights, but also a vision for his future. He had absorbed the methods of Cambridge and Manchester, seen the forefront of atomic research, and understood the challenges and opportunities that lay ahead. He was still a young man, only in his late 20s, but he carried the confidence of someone who had tested himself against the best in Europe. In Copenhagen, he accepted a post at the university, gradually rising through its ranks. His lectures revealed a style that was distinctly his own. He was not a flamboyant speaker. Instead, he spoke with pauses, hesitations, and thoughtful repetitions, as if he were thinking aloud. For some, this made his lectures difficult to follow, but for others, it was a window into the workings of a profound mind. Students who listened carefully often remarked that behind the halting words lay insights of extraordinary depth. Bohr's approach to education, both as a student and later as a teacher, reflected his belief that learning was not about memorizing facts, but about wrestling with problems. He encouraged his students to challenge assumptions, to ask questions that seemed almost naïve, and to be unafraid of paradox. These habits were deeply rooted in his own formative years, where persistence and curiosity had guided him more than brilliance or quickness. By the mid-1910s, Bohr was ready to embark on the work that would make him famous, the Bohr model of the atom. But to understand how he reached that point, one must look back at the long thread of his early life, the influence of his father's laboratory, the quiet intellectual climate of his family, the rigorous education of Copenhagen, the philosophical reflections that shaped his thinking, and the formative experiences in Cambridge and Manchester. All of these strands wove together into a mind uniquely prepared to confront the mysteries of atomic structure. Looking back, it is remarkable to see how much of Bohr's later greatness can be traced to these early years. His humility came from his family upbringing, where dialogue and curiosity were valued more than pride. His persistence came from his school days, where he learned to think slowly and carefully. His boldness came from his doctoral research, where he dared to challenge established theories. His philosophical bent came from his fascination with Kierkegaard and the Danish tradition of thought. His international perspective came from his travels, where he learned from the leading scientists of his age. And his stability came from his marriage to Margrethe, who would stand by him through the triumphs and the trials that lay ahead. By 1913, the young man from Copenhagen, who once built makeshift instruments to study surface tension, was on the verge of publishing a paper that would change physics forever. But that is another story. The tale of his early life and education closes here, with a portrait of a thinker shaped by his family, his city, his teachers, and his times, standing at the edge of greatness. It is a reminder that even the most revolutionary ideas do not spring from nowhere. They are the product of years of quiet preparation, of influences seen and unseen, of struggles and small victories that lay the groundwork for transformation. The story of Niels Bohr's early life is not merely the story of a student becoming a scientist. It is the story of a human being shaped by curiosity, nurtured by family, tested by mentors, and strengthened by love. It is the story of how the father of quantum theory was, before all else, a son of Copenhagen, a child of inquiry, and a seeker of truth. And in this story lies the foundation of everything that followed: the model of the atom, the principle of complementarity, and the reshaping of science itself. At the dawn of the 20th century, the atom was no longer a philosophical abstraction but a scientific puzzle demanding an answer. For centuries, thinkers had imagined the atom as an indivisible particle, the smallest building block of matter, a concept first whispered by the ancient Greeks. But by the time Niels Bohr entered the scientific world, the atom had begun to reveal secrets far stranger than anyone had imagined. The electron, discovered in 1897 by J.J. Thomson, showed that the atom was not indivisible at all. A decade later, Ernest Rutherford's gold foil experiment demonstrated that most of the atom was empty space, with nearly all its mass concentrated in a tiny, dense nucleus. Yet, despite these breakthroughs, the picture of the atom was incomplete, unstable, and confusing. It was into this uncertain terrain that Niels Bohr stepped, carrying with him not only the education and philosophy of his Danish upbringing, but also a bold imagination that would give the world a new vision of atomic structure. In 1912, when Bohr joined Rutherford in Manchester, the atmosphere of the laboratory was electric with discovery. Rutherford's model had shaken physics to its core, a miniature solar system in which electrons revolved around a central nucleus, much like planets orbiting the sun. It was a daring image, simple and elegant, but it contained a fatal flaw. According to the laws of classical physics, especially the rules of electromagnetism formulated by James Clerk Maxwell, electrons moving in circular orbits should constantly emit radiation, lose energy, and spiral into the nucleus. If this were true, the atom could not exist for more than a fraction of a second. Matter itself, as people understood it, would collapse. Clearly, something was missing. Bohr recognized the problem immediately. His training in Copenhagen, coupled with his exposure to Rutherford's experiments, made him acutely aware of the limitations of classical theory. At the same time, he was deeply familiar with the revolutionary ideas that Max Planck and Albert Einstein had introduced. Planck, in 1900, had suggested that energy was not continuous but came in discrete packets called quanta. Einstein, in 1905, had expanded this notion to explain the photoelectric effect, proposing that light itself behaved as if it were composed of quanta, later called photons. These ideas, still considered radical, provided the seeds that Bohr would cultivate into something extraordinary. The young Dane began to think differently about the atom. If classical physics predicted instability, then perhaps the atom did not obey classical rules at all. Perhaps the behavior of electrons was governed by new principles that acknowledged the strange reality of quanta. Slowly, through discussions, calculations, and long hours of thought, Bohr began to shape a new model. The breakthrough came in 1913, in a trilogy of papers published under the title, On the Constitution of Atoms and Molecules. Bohr presented an atomic model that would soon become famous. At its heart was a daring proposal: electrons could occupy only certain discrete orbits around the nucleus, and while in these orbits, they did not radiate energy. Only when an electron jumped from one orbit to another would it emit or absorb radiation, and the energy of this radiation corresponded precisely to the difference between the two orbits. It was a revolutionary idea. No one had ever imagined that electrons could move in such quantized paths, immune to the rules of classical mechanics. Bohr had taken the concept of quanta and woven it into the very fabric of atomic structure. In doing so, he solved the riddle of atomic stability. Electrons no longer spiraled into the nucleus. Instead, they resided in stable orbits defined by quantum conditions. Matter, as it turned out, existed because of this strange new law of nature. Yet Bohr's contribution was not merely theoretical elegance. His model explained real experimental puzzles that had baffled scientists for decades. One of the greatest mysteries of the time was the spectrum of hydrogen, the simplest atom. When hydrogen gas was heated or electrified, it emitted light at specific wavelengths, producing a series of bright lines when passed through a prism. This line spectrum was well documented, but classical physics could not explain it. Bohr's model did. By calculating the allowed energy levels of hydrogen's electron orbits, Bohr derived a formula that matched the observed spectral lines with astonishing accuracy. Suddenly, the mysterious patterns of light became a window into the structure of the atom. The scientific world was stunned. Here was a theory that not only saved Rutherford's nuclear atom from collapse, but also explained the hydrogen spectrum in precise detail. It was a triumph of imagination, mathematics, and experimental relevance. Bohr, still in his 20s, had placed himself among the leading physicists of his generation. His papers quickly spread across Europe, and the Bohr model became a phrase spoken in every physics classroom and laboratory. But like all great advances, the Bohr model also raised questions. How could electrons jump between orbits without traversing the space in between? What determined which orbits were allowed? And how could this model apply to atoms more complex than hydrogen? These mysteries did not diminish Bohr's achievement. Rather, they illuminated the frontier of a new science that was just being born: quantum mechanics. Bohr himself was well aware of the limitations of his model. He did not see it as the final answer, but as a step forward, a bridge between the old world of classical physics and the new quantum reality. His humility was evident in the way he described his work, not as a completed theory but as a framework to be tested, refined, and extended. Yet his confidence in the core idea, that atomic behavior required a new kind of law, never wavered. In Copenhagen, Bohr continued to develop his ideas, often in collaboration with colleagues and students. His style of work was conversational, even philosophical. He enjoyed sitting with young physicists, debating problems late into the night, sketching equations on scraps of paper, and exploring not just the technical aspects of atomic theory, but also its deeper implications. To Bohr, the atom was not merely a physical object, it was a symbol of nature's paradoxes, a reminder that human understanding would always be partial and provisional. The impact of Bohr's contributions to atomic structure was immediate and profound. Chemistry, which had long relied on the concept of atoms as indivisible units, now gained a theoretical foundation that explained why atoms behaved as they did in forming molecules and compounds. Physics, once confined by the limits of classical mechanics, was open to an entirely new landscape. Even technology began to feel the ripple effects, as the understanding of atomic spectra and energy levels laid the groundwork for fields that would later blossom into electronics, lasers, and quantum computing. What is striking in Bohr's story is not only the brilliance of his ideas, but also the intellectual courage required to propose them. At the time, the suggestion that electrons occupied quantized orbits was almost unthinkable. It defied intuition, it contradicted centuries of mechanical tradition, and it required scientists to accept that nature operated on principles fundamentally different from the ones they had trusted. Many resisted at first, skeptical of this new model. But Bohr's success with hydrogen spectra was undeniable, and gradually the physics community began to embrace his vision. Behind the public recognition lay countless hours of solitary effort. Bohr was known to immerse himself so deeply in his work that he often forgot the world around him. Friends and family recalled that he could sit silently for hours, lost in thought, his eyes distant, his mind turning over problems like stones in a river. Then, suddenly, he would leap to his feet, seized by a new idea, eager to test it or explain it. These moments of inspiration were the fruit of relentless persistence, of a mind that refused to let go until the problem yielded. By the mid-1910s, the Bohr model had become the cornerstone of atomic theory. It appeared in textbooks, lectures, and scientific discussions worldwide. For students of physics, it was often the first glimpse into the strange and beautiful world of quantum ideas. For chemists, it provided clarity about the periodic table and the behavior of elements. For physicists, it was a promise that the mysteries of the atom could be solved, if only they dared to think beyond classical limits. Yet for Bohr himself, the work was only beginning. He understood better than anyone that his model was incomplete. The world of atoms was not yet fully mapped, and the principles that governed electrons were still shrouded in mystery. But his contributions to atomic structure had given science a compass, a direction, a vision of how to proceed. It was a gift not only of knowledge but of imagination, a reminder that the path to truth often lies in daring to believe the unbelievable. Thus, the early years of Niels Bohr's contributions to atomic structure stand as one of the most remarkable episodes in the history of science. They show how a young man, armed with the lessons of his education and the courage of his convictions, reshaped humanity's understanding of matter itself. And they remind us that sometimes the smallest objects, the atoms invisible to the naked eye, can open the largest doors to knowledge, doors that lead into the very heart of reality. The success of Niels Bohr's atomic model in 1913 marked only the beginning of a scientific journey that would transform not just physics but the way humanity thought about nature. The Bohr model had given the atom a structure that could be calculated, predicted, and tested, and for the first time, the strange behavior of electrons was linked to the newly emerging concept of quantum theory. Yet as the acclaim spread across Europe, Bohr himself remained cautious. He understood that while his model explained hydrogen with elegance, the universe was filled with atoms far more complex, and for those, his theory was not yet enough. The scientific community received his work with a mixture of admiration and skepticism. Admirers were dazzled by the way his calculations matched hydrogen's spectral lines so perfectly, while skeptics pointed to the unanswered questions. Why should electrons be restricted to certain orbits in the first place? What was the underlying principle that dictated these quantized paths? Bohr himself could not fully answer. He presented his model as a provisional step, a working hypothesis that would one day be explained more deeply. His humility in this regard was unusual, for he did not claim final truth but instead offered a framework, a scaffolding on which others could build. Among those who took up the challenge were physicists across Europe, each bringing their own perspective. Arnold Sommerfeld in Munich refined Bohr's model by introducing elliptical orbits instead of simple circles, extending the theory to explain more complex atomic spectra. These refinements improved accuracy, but also highlighted the growing complexity of the task. The atom, once thought of as simple, revealed itself to be a universe of motion, energy, and uncertainty. For Bohr, the challenge was not only scientific, but also philosophical. He had grown up steeped in the Danish tradition of thought, influenced by Kierkegaard, and the idea that human understanding was always partial, always framed by paradox. The atom seemed to embody this very principle. On one hand, it behaved like a miniature solar system with electrons orbiting a nucleus. On the other hand, it refused to follow the rules of classical mechanics. Bohr began to see the atom not as a mechanical object but as a symbol of a new reality, one in which observation and knowledge themselves played a central role. The years following his 1913 papers were filled with both triumph and tension. He traveled widely, presenting his ideas at conferences, meeting with other leading physicists, and engaging in debates that often stretched late into the night. His personality was distinctive, modest, thoughtful, hesitant in speech, yet unyielding in his pursuit of clarity. He would often pause mid-sentence, searching for the exact word, sometimes circling around an idea before finally landing on it with precision. To some, this made him difficult to follow; to others, it was evidence of a mind that refused to settle for superficial explanations. In Copenhagen, Bohr continued to refine his theories, while also establishing himself as a teacher and mentor. He attracted students from around the world, drawn by the promise of working with a thinker who was reshaping atomic science. His style of mentorship was unlike that of many professors. He encouraged open discussion, welcomed challenges to his ideas, and treated even the youngest students as partners in exploration. The atmosphere he cultivated was one of intellectual freedom, where questions were more valuable than answers, and where every paradox was an opportunity rather than a problem. The importance of his contributions to atomic structure went beyond the immediate explanation of hydrogen spectra. By proposing that electrons existed in quantized orbits, Bohr had introduced a new principle into science: that nature itself was not continuous but discrete at its most fundamental level. This was a radical break from centuries of thinking, and it prepared the ground for the full development of quantum mechanics in the 1920s. Without Bohr's model as a stepping stone, the path to Heisenberg's uncertainty principle, Schrödinger's wave mechanics, and Dirac's quantum theory might have been much longer and more uncertain. Yet Bohr's own involvement in this next phase was crucial. In the 1920s, as younger physicists like Werner Heisenberg and Wolfgang Pauli began to extend and challenge his model, Bohr welcomed them to Copenhagen. His institute became a center of the quantum revolution, a place where ideas were tested, debated, and often transformed. Here, Bohr's contributions to atomic structure evolved into something larger, not just a model of the atom, but a philosophy of science itself. One of Bohr's most profound contributions during this period was the principle of complementarity. Though it would become most famous in the context of quantum mechanics, its roots lay in his work on atomic structure. Complementarity proposed that phenomena at the atomic level could display seemingly contradictory properties, such as being both a particle and a wave, depending on how they were observed. Rather than seeing this as a failure of understanding, Bohr saw it as a fundamental feature of reality. The atom, in his view, was not something that could be fully captured by a single picture. It demanded multiple perspectives, each valid but incomplete. This way of thinking reshaped not only atomic physics, but also the philosophy of science. It suggested that human knowledge was inherently limited, that the observer could not be separated from the observed, and that reality at the atomic level was richer and more subtle than classical images could convey. Bohr's model of the atom was thus more than a technical theory. It was a gateway into a new way of seeing the universe. The legacy of his contributions to atomic structure can also be traced through their impact on chemistry. For decades, chemists had organized the elements in the periodic table without a clear understanding of why they followed such a pattern. Bohr's atomic model provided the key. The arrangement of electrons in quantized orbits determined the chemical properties of each element. The periodic table was no longer a mysterious pattern, but a reflection of the atom's internal architecture. This insight bridged physics and chemistry, uniting two fields that had long been separate. But even as his ideas gained global recognition, Bohr never allowed himself to be swept away by fame. He remained the same thoughtful man who valued dialogue over dominance, cooperation over competition. Colleagues recalled that in discussions, he would often listen more than he spoke, and when he did speak, it was with an openness that invited further questions rather than closing them. His institute in Copenhagen became not only a scientific hub but also a community where collaboration thrived. As the 1920s gave way to the 1930s, the limitations of the Bohr model became more apparent. For complex atoms with many electrons, the simple picture of quantized orbits was no longer sufficient. Wave mechanics, developed by Schrödinger, and matrix mechanics, pioneered by Heisenberg, offered more precise descriptions. Yet Bohr's contributions remained foundational. Without his vision of quantized orbits, the leap to full quantum mechanics might not have been possible. His work had opened the door, and others had walked through, but the door itself bore his name. Even when newer theories surpassed his own, Bohr accepted this with grace. He never clung to the past, but instead embraced the future, seeing each advance as a continuation of the journey he had begun. To him, science was not about personal glory, but about the collective effort to understand nature. He once remarked that the opposite of a great truth may also be a great truth, a statement that captured his belief in paradox, complementarity, and the ever-evolving nature of knowledge. By the time the world entered the turbulent decades of war and upheaval, Bohr's contributions to atomic structure had already secured his place in history. Yet his role continued to expand as he advised on nuclear research, reflected on the ethical implications of science, and engaged with leaders across the globe. The atom, which he had helped make visible to human thought, was now both a source of wonder and a source of fear, capable of lighting cities or destroying them. Bohr understood this duality deeply, and it added a moral dimension to his lifelong engagement with the atom. Looking back at his contributions to atomic structure, one sees not just a scientific achievement but a human story. It is the story of a man who dared to question, who embraced uncertainty, who believed that even the smallest particle contained mysteries worthy of a lifetime's pursuit. His model of the atom may have been replaced by more advanced theories, but its spirit endures. In the textbooks that still teach it as the first step into quantum theory, in the laboratories that continue to probe the atom's secrets, and in the minds of all who see science as a dialogue between imagination and reality. In the end, Niels Bohr's contributions to atomic structure remind us that science is not merely about equations or experiments. It is about vision, courage, and the willingness to accept that nature may be stranger than we can ever fully comprehend. Bohr gave the world not just a model of the atom, but a model of thought itself, one that embraced complexity, welcomed paradox, and sought truth with humility, and in doing so, he helped humanity take one of its greatest steps toward understanding the invisible architecture of the universe. In the early years of the 20th century, the atom stood as one of the greatest mysteries of science. Physicists had probed deeper into nature than ever before, uncovering a subatomic world that both fascinated and unsettled them. Atoms, once thought to be indivisible particles of matter, had revealed themselves to contain inner landscapes of extraordinary complexity. J.J. Thomson's discovery of the electron had shown that atoms were not solid spheres, but structures with moving parts. Ernest Rutherford's scattering experiments had revealed the dense nucleus, small yet heavy, occupying the center of the atom while electrons moved somewhere outside it. These discoveries were milestones, but they also created a puzzle. If electrons orbited the nucleus like planets around the sun, as Rutherford imagined, why did atoms not collapse? According to classical physics, those orbiting electrons should continuously radiate energy, spiraling inward until the atom disintegrated in a fraction of a second. Clearly, something was missing. It was in this landscape of uncertainty that Niels Bohr, a young physicist from Copenhagen, presented an idea that would change the course of science. The Bohr model of the atom, introduced in 1913, was more than a scientific paper. It was a turning point in humanity's understanding of matter itself. Bohr's model was daring, counterintuitive, and in many ways incomplete. But it achieved something no one else had. It gave the atom stability and explained its spectral fingerprint with mathematical precision. The story of the Bohr model begins in Manchester, in the laboratory of Ernest Rutherford. Bohr had traveled there after a frustrating stint in Cambridge, drawn by Rutherford's energy and openness. Rutherford had already shaken the scientific world with his nuclear atom, a dense, positively charged nucleus orbited by tiny negative electrons. Bohr admired the boldness of the idea, but he also saw its flaw. Classical physics could not keep the electrons from crashing into the nucleus. Bohr, with his background in both experimental skill and theoretical imagination, began to wonder whether a new principle was needed, one that did not obey the classical laws of motion, but something entirely different. At this time, the strange new concept of quantization was slowly gaining attention. Max Planck in 1900 had introduced the idea of energy quanta to explain blackbody radiation, a concept so radical that even he viewed it as a mathematical trick rather than a true law of nature. Albert Einstein, 5 years later, had applied this quantization to light itself, proposing that light behaved as if it were made of particles, quanta of energy later called photons. These ideas hovered at the edges of physics, controversial and unsettling. Bohr, however, took them seriously. He wondered, if energy in light came in discrete packets, perhaps energy in the atom did as well. Out of this bold speculation emerged the Bohr model. In a trilogy of papers titled On the Constitution of Atoms and Molecules, Bohr laid out his vision. The atom, he proposed, was not a miniature solar system obeying classical rules. Instead, electrons occupied certain specific orbits around the nucleus, and these orbits were quantized. That is, only certain orbits were allowed, and while in these orbits, the electrons did not radiate energy. They were stable. An electron could jump from one orbit to another, and in doing so it would absorb or emit a quantum of energy equal to the difference between the orbits. This emission of energy would appear as light, and the frequency of that light was given by a simple equation derived from Planck's quantum hypothesis. With this idea, Bohr solved two problems at once. First, he explained why atoms were stable. Electrons could not spiral inward because they were restricted to fixed orbits. Second, he explained the spectral lines of hydrogen. The hydrogen atom, with its single electron, had a simple and well-documented spectrum consisting of sharp lines at specific wavelengths. Classical physics had failed to account for these lines, but Bohr's model predicted them exactly. His equation matched the observed spectrum with uncanny precision, transforming what had been a mystery into a triumph of theory. The effect on the scientific community was electrifying. Here was a model that not only gave the atom a structure, but also explained experimental data with mathematical clarity. For decades, scientists had recorded the spectral patterns of hydrogen without knowing why they occurred. Bohr's model turned those mysterious lines into evidence for a new picture of reality. Suddenly, the atom was no longer a vague idea, but a calculable system governed by principles that could be tested and applied. Yet the Bohr model was not merely a technical achievement, it was also a conceptual leap. Bohr had introduced into physics the idea that certain laws of nature could not be explained by classical reasoning. Electrons did not radiate in their stable orbits, not because of some hidden mechanism, but because this was a fundamental law. To classical physicists, this was a shocking statement. How could one simply declare that the rules were different without offering a deeper explanation? But Bohr, with his philosophical sensibility, understood that sometimes science required a leap into the unknown, a willingness to accept new rules when old ones failed. The Bohr model quickly became a cornerstone of physics education. Students around the world learned to draw atoms with circular electron orbits, each orbit corresponding to a specific energy level. They learned that when an electron jumped from a higher orbit to a lower one, a photon of light was emitted, and the color of that light could be calculated. For the first time, atomic physics entered the classroom as a tangible subject, one that could be visualized and quantified. But behind the diagrams lay deeper implications. The Bohr model suggested that nature was not continuous but discrete. The energy of electrons came in steps, not in smooth gradients. This discreteness was a profound break from centuries of thinking, a shift that would echo throughout physics, chemistry, and eventually technology. It laid the foundation for quantum mechanics, which would soon emerge as the most revolutionary scientific theory of the 20th century. Bohr himself, however, was aware of his model's limitations. It worked beautifully for hydrogen, with its single electron, but for more complex atoms it struggled. Attempts to extend the model to helium or heavier elements required increasingly complex assumptions. Other physicists, such as Sommerfeld, modified the model by introducing elliptical orbits, adding layers of refinement that improved accuracy, but also revealed how fragile the model was. Bohr did not resist these changes. Instead, he welcomed them, seeing his model not as a final truth, but as a step toward a deeper theory. In Copenhagen, Bohr continued to reflect on the meaning of his work. He was not satisfied with simply producing equations. He wanted to understand what they implied about reality. He asked questions that others avoided. What does it mean for an electron to jump from one orbit to another? Does it travel through space between the orbits, or does the jump happen instantaneously? What does it mean that an orbit is allowed? These questions pushed him toward a philosophy of science that would later crystallize into his principle of complementarity. But even in 1913, the seeds of this thinking were present. The Bohr model also carried enormous significance for chemistry. The arrangement of electrons in orbits explained why elements behaved as they did, why some combined easily and others did not, why the periodic table followed its mysterious order. Chemistry, once an empirical science of reactions and compounds, now had a theoretical foundation rooted in the structure of the atom. Bohr had not only explained physics, but had also united it with chemistry in a way that reshaped both disciplines. Outside the scientific community, the Bohr model captured the imagination of the public. Newspapers reported on the young Danish physicist who had given the world a new atom. Popular science writers described electrons jumping between orbits, emitting flashes of light, a cosmic dance at the heart of matter. For a world that was just beginning to embrace modernity, the atom became a symbol of progress, a glimpse into the hidden machinery of reality. Bohr, however, remained modest. Fame did not alter his quiet demeanor. He continued to work in his office in Copenhagen, surrounded by students and colleagues, engaging in long discussions about the nature of the atom. His genius lay not only in his ideas, but in his ability to foster collaboration, to create an environment where questions were welcomed, and where even the most radical thoughts could be explored. By the time the First World War disrupted Europe, Bohr's model had already secured its place in the annals of science. While the war raged, the atom remained in laboratories and lecture halls, a symbol of knowledge unshaken by political turmoil. Bohr's model endured because it worked, because it explained what others could not, and because it pointed toward a new future for physics. The Bohr model of the atom, in its simplicity and its daring, stands as one of the great achievements of human thought. It was not the final word, but it was a first word, a necessary step into a world where certainty gave way to probability, where continuity gave way to discreteness, and where classical laws gave way to quantum rules. It was a bridge between two eras, built by a young man who dared to believe that the atom could be understood in a new way. And though later theories would surpass it, the Bohr model remains etched in the history of science, taught in classrooms, remembered in diagrams, and revered as the moment when the atom first revealed its secrets to human eyes. It was, in many ways, the birth of modern atomic physics, and its author, Niels Bohr, became its most eloquent interpreter. The years after Bohr introduced his model were a time of rapid change and continuous testing. The Bohr model had struck a deep chord because it gave order to a chaotic puzzle, but the scientific world does not accept beauty alone. Predictions had to be verified, and every detail had to withstand the probing eyes of experimenters. Hydrogen, the simplest atom, had already offered a stunning confirmation of Bohr's theory. The calculated energy levels matched the observed spectral lines with such precision that even skeptics paused. Still, physicists knew that hydrogen was only the beginning. If the model was truly fundamental, it needed to hold for more complicated atoms, for ionized species, and for the chemistry of the periodic table. In Munich, Arnold Sommerfeld extended Bohr's circular orbits to elliptical ones, introducing the idea of sublevels within each principal orbit. This adjustment allowed the model to explain fine details of atomic spectra, such as the splitting of lines into closely spaced groups. Sommerfeld's refinements also incorporated aspects of Einstein's theory of relativity, further expanding the reach of Bohr's ideas. The collaboration between Bohr's bold vision and Sommerfeld's mathematical precision revealed the flexibility of the model. It could grow, adapt, and absorb new concepts, but this very flexibility also hinted at its fragility. If so many additions were required, perhaps the model was not the final architecture of the atom, but a temporary scaffolding. Despite its limitations, the Bohr model quickly became a powerful tool. In chemistry, it explained the periodic table in terms of electron arrangements. Each element's chemical properties could be traced to the structure of its outermost orbit. Suddenly, The mysterious, repeating patterns of the periodic table, charted by Dmitri Mendeleev decades earlier, had a physical explanation. Why did the noble gases resist combining with other elements? Because their outer orbits were filled. Why did sodium and potassium behave similarly? Because each had a single electron in their outermost orbit, ready to be given up in reactions. This was not just physics, it was the unification of two sciences that had long developed in parallel. Bohr's model provided the missing key, turning chemistry into a branch of atomic physics. The cultural resonance of this achievement was immense. For centuries, the atom had been an abstract philosophical idea, debated by Greeks and speculated upon by Enlightenment thinkers. Now, it had a structure that could be drawn, calculated, and connected directly to the world of experiment. Diagrams of atoms with neat concentric orbits appeared in textbooks, popular science magazines, and even advertisements. To the public, Bohr's atom became an icon of modern science, a symbol of the hidden order underlying reality. Yet, within the physics community, debate continued. The Bohr model could not fully explain spectra of elements beyond hydrogen and helium. As the complexity of atoms increased, the orbits multiplied, and the predictions became less precise. Moreover, the very concept of electrons moving in fixed orbits seemed at odds with the emerging evidence of their wave-like behavior. In 1924, Louis de Broglie proposed that electrons, like light, could behave as waves. This idea, startling in its simplicity, suggested that Bohr's orbits were not rigid tracks but standing waves circling the nucleus. In this view, only certain wavelengths could fit around the nucleus, giving rise to the quantized orbits Bohr had described. It was a profound insight, one that provided a physical justification for Bohr's quantum jumps, but it also signaled the beginning of a shift away from the orbital picture. In Copenhagen, Bohr embraced these new developments. He never clung possessively to his model, but instead welcomed challenges, seeing them as opportunities to deepen understanding. When Werner Heisenberg arrived in 1924, Bohr encouraged him to rethink the atom entirely. Heisenberg's matrix mechanics, developed in Bohr's institute, abandoned the notion of visualizable orbits altogether. Instead, it described atoms in terms of mathematical relations among observable quantities. Soon after, Erwin Schrödinger introduced wave mechanics, presenting the atom as a system of waves rather than particles in fixed paths. Both approaches went beyond Bohr's model, yet both grew out of the soil he had cultivated. This period, often called the quantum revolution, would have been unthinkable without the Bohr model. It was Bohr's daring step in 1913 that had broken the stranglehold of classical mechanics on atomic theory. His insistence on quantization, his willingness to declare that certain orbits simply existed without classical explanation, had prepared the way for the radical departure that followed. Even as his own model was surpassed, Bohr's role as midwife to quantum mechanics was recognized by all. Philosophically, the Bohr model had already hinted at themes that would dominate quantum theory. The idea that electrons could jump from one orbit to another without passing through intermediate states was not just a physical oddity, it was a challenge to the very concept of continuity. For centuries, science had assumed that change was gradual, that processes unfolded smoothly in time and space. Bohr's atom shattered that assumption, introducing the idea of discontinuous change, of quantum leaps. Later, when Heisenberg formulated the uncertainty principle and Bohr articulated complementarity, these ideas of discontinuity and paradox found their mature form. But they were already implicit in the Bohr model. In the 1920s and 1930s, Bohr often reflected on how his model had been received. Some had criticized it as arbitrary, others had praised it as revolutionary. For Bohr, it was neither triumph nor failure, but a stage in the unfolding of knowledge. He frequently reminded his students that models are not mirrors of reality, but tools for thought, approximations that help guide us toward deeper truths. The Bohr model, in this sense, was a scaffolding, a structure that would be taken down once the building of quantum mechanics was complete, but without which the building could not have been raised. The influence of the Bohr model extended far beyond physics and chemistry. In the broader culture, it became a metaphor for order emerging from chaos, for the hidden structure of the universe. Artists, writers, and philosophers drew inspiration from the image of the atom with its circling electrons. The model appeared in popular art, on book covers, in political cartoons, and even in jewelry designs. For a society moving rapidly into modernity, the atom as envisioned by Bohr was both mysterious and reassuring. Mysterious because it revealed a hidden world unlike anything visible to the senses, and reassuring because it suggested that this world was governed by law, by patterns that could be understood. Bohr himself remained cautious about such cultural appropriations. He knew that his model was provisional, that the true nature of the atom was even stranger than concentric circles suggested. But he also recognized the value of metaphors, of images that could carry complex ideas into the public imagination. He often spoke not only as a physicist but as a philosopher, emphasizing that science was a human endeavor shaped by language, concepts, and the limits of our perception. The Bohr model, in this broader view, was not only a scientific achievement but also a cultural artifact, a symbol of humanity's attempt to peer into the invisible. By the 1930s, the Bohr model had been absorbed into the larger framework of quantum mechanics. The concept of fixed orbits gave way to probability clouds, and the precise jumps of electrons became transitions between quantized energy states described by wave functions. Yet the Bohr model did not disappear. It remained in textbooks as an introduction, a simplified picture that students could grasp before confronting the abstract mathematics of modern theory. Even today, a century later, schoolchildren around the world first encounter the atom through diagrams that echo Bohr's vision. Though outdated as a literal description, it remains pedagogically powerful, a gateway to deeper understanding. For Bohr himself, the model was a source of lasting satisfaction. Not because it was perfect, but because it had opened the door to a new way of thinking. He often emphasized that the value of a theory lies not only in its correctness, but in its ability to inspire, to provoke new questions, to shape the path of inquiry. The Bohr model had done all of this. It had explained hydrogen, illuminated the periodic table, and pointed the way to quantum mechanics. It had transformed both science and culture, leaving a legacy far greater than its technical details. In retrospect, the Bohr model represents a moment of profound transition. It stands at the threshold between the classical and the quantum, between certainty and uncertainty, between continuity and discontinuity. It was a model born of paradox, one that embraced the impossibility of explaining everything within classical rules and dared instead to impose new ones. In doing so, it revealed that nature was deeper, stranger, and more beautiful than anyone had imagined. The story of the Bohr model is not just the story of an equation or a diagram. It is the story of a young scientist daring to trust his intuition, to borrow ideas from the margins of physics, and to propose a vision that seemed almost absurd at the time. It is the story of a community grappling with the implications of that vision, refining it, extending it, and ultimately moving beyond it. It is the story of science itself, tentative, provisional, always reaching beyond its grasp, always willing to replace old truths with new ones. When we look at the atom today, through the lens of quantum mechanics and particle physics, Bohr's concentric circles may seem quaint. Yet without them, the path to our modern understanding would have been far longer and more difficult. The Bohr model, with its elegant simplicity, provided the first clear picture of the atom as a structured, quantized system. It remains a monument to the power of imagination, to the courage of questioning, and to the enduring quest to understand the invisible foundations of the universe. And so, in the grand narrative of science, the Bohr model holds a unique place, not as the final answer but as a decisive step, not as the whole truth, but as a necessary truth along the way. It is a reminder that even the most provisional theories can change the world, that sometimes the simplest drawings can capture the deepest mysteries, and that the journey of knowledge is built not on certainty, but on daring leaps into the unknown. In the 1920s, the landscape of physics was shifting in ways that few could have anticipated. At the heart of this transformation stood Niels Bohr, already celebrated for his model of the atom, but now faced with a scientific revolution that would demand even greater imagination. The Bohr model had provided stability to the atom and explained hydrogen's spectrum, but its limits were clear. To understand the complexity of heavier atoms and to resolve the contradictions between waves and particles, a deeper theory was required. Out of this need arose quantum mechanics, a framework that would redefine science itself, and Bohr was both a participant and a philosopher of this new order. The seeds of quantum mechanics had already been sown by Planck and Einstein, but the breakthrough came in the mid-1920s. Werner Heisenberg, working under Bohr's guidance in Copenhagen, developed matrix mechanics, a daring approach that abandoned visualization of atomic paths and focused instead on observable quantities. Almost simultaneously, Erwin Schrödinger introduced wave mechanics, offering a picture of electrons as waves spread through space, bound by the nucleus. At first, these two approaches seemed irreconcilable, mathematical abstractions on one side, wave pictures on the other, but both described the atom with remarkable accuracy, surpassing the limitations of Bohr's orbits. Bohr watched these developments with both excitement and caution. His instinct was not to choose between Heisenberg and Schrödinger, but to find a way of uniting their perspectives. Out of this effort emerged one of his most enduring contributions, the principle of complementarity. Bohr argued that the electron could be described as either a particle or a wave, but never both at the same time. Each description was valid, yet incomplete, and only by accepting their complementarity could one grasp the full truth of quantum phenomena. This idea went beyond physics. It suggested that human knowledge itself was limited, that reality revealed itself in mutually exclusive ways depending on how we ask the question. The debates of this era were fierce, and none were more famous than those between Bohr and Einstein. Einstein, though one of the founders of quantum theory, was deeply troubled by its implications. He rejected the idea that probability and uncertainty could be fundamental features of nature. His famous words, "God does not play dice," captured his discomfort. Bohr, in contrast, defended the probabilistic nature of quantum mechanics with equal passion. In a series of legendary encounters, particularly at the Solvay conferences of the late 1920s, the two men sparred over the meaning of the new theory. Einstein proposed thought experiments designed to reveal contradictions in quantum mechanics. Bohr countered each with careful reasoning, showing that quantum theory remained consistent even if it defied common sense. These debates were more than academic arguments. They represented two worldviews: Einstein's belief in an underlying determinism and Bohr's conviction that uncertainty and complementarity were woven into the fabric of reality. In the end, history favored Bohr's interpretation. Quantum mechanics flourished under the Copenhagen interpretation, as it came to be known, emphasizing probability, measurement, and complementarity as central principles. Bohr's role in shaping this interpretation was decisive, making him not only a builder of atomic models, but also the philosopher of the quantum age. The influence of Bohr in this period extended far beyond his own writings. His institute in Copenhagen became the crucible of quantum mechanics. Young physicists from around the world flocked there, drawn by the chance to work with Bohr and to participate in the revolution. Heisenberg, Pauli, Dirac, and many others spent formative years in his orbit, absorbing not only his ideas but also his way of thinking. Bohr's style was unique. He encouraged debate, welcomed disagreement, and treated every question as an opportunity. Conversations often stretched late into the night, filled with pauses, reconsiderations, and the relentless search for clarity. To his students, these discussions were as important as equations, shaping how they thought about science and about truth itself. The philosophical depth of Bohr's approach gave quantum mechanics a character that extended beyond the laboratory. Complementarity was not merely a tool for describing atoms, it became a way of thinking about life, knowledge, and human existence. Bohr himself drew parallels between physics and other fields, suggesting that complementarity could illuminate psychology, biology, and even philosophy. Though controversial, these reflections revealed the breadth of his vision. For Bohr, quantum mechanics was not just a theory of particles, but a window into the limits and possibilities of human understanding. As the new mechanics matured, Bohr's role shifted from innovator to interpreter, from model builder to guide. He did not contribute equations as dazzling as Schrödinger's or as abstract as Heisenberg's, but he gave the theory coherence. His insistence on the centrality of measurement, on the inseparability of observer and observed, framed the way generations of physicists thought about the quantum world. Without Bohr, quantum mechanics might have remained a set of mathematical tools. With him, it became a worldview. The practical consequences of this revolution soon followed. Quantum mechanics provided the basis for chemistry, solid-state physics, electronics, and later nuclear physics. The technologies of the modern world, from semiconductors to lasers to quantum computers, trace their lineage back to these breakthroughs. At the heart of that lineage stands Niels Bohr, whose vision gave the atom structure, whose philosophy gave quantum mechanics meaning, and whose leadership turned Copenhagen into the birthplace of the quantum age. Bohr's engagement with quantum mechanics did not end with theory. He was deeply concerned with its broader implications, especially as the atom became the basis for nuclear weapons. The same understanding of nuclei and quantum behavior that began with his model of the atom eventually led to the splitting of uranium and the release of atomic energy. Bohr recognized both the promise and the peril of this knowledge. In the years that followed, he became not only a physicist but a statesman of science, advocating for openness, dialogue, and the responsible use of nuclear power. Looking back, one sees that Bohr's role in quantum mechanics was not to provide all the answers, but to teach the world how to live with questions. He accepted paradox, embraced uncertainty, and turned them into tools for discovery rather than obstacles. His principle of complementarity remains one of the most profound ideas in science, a reminder that reality is richer than any single description and that truth may come in fragments rather than absolutes. In the end, Bohr's legacy in quantum mechanics is inseparable from the theory itself. He was its architect, its interpreter, its philosopher, and its guardian. Where others sought certainty, he found meaning in ambiguity. Where others resisted probability, he saw a new order. Where others demanded clear images, he accepted that nature defied visualization. It was this humility, this willingness to let nature speak in its own strange language, that defined Bohr's contribution. And so the story of Niels Bohr and quantum mechanics is not simply the tale of equations and experiments. It is the story of a man who gave humanity a new way of seeing, who transformed uncertainty into knowledge, and who taught us that even at the smallest scales, the universe is full of mystery, beauty, and paradox. In the history of science, few ideas have been as daring and as unsettling as Niels Bohr's principle of complementarity. It emerged not from a single experiment or equation, but from a long struggle to understand the paradoxical behavior of nature at the atomic scale. By the mid-1920s, quantum mechanics had begun to take shape, offering astonishingly accurate descriptions of atomic phenomena, but the theory came at a heavy philosophical price. Electrons behaved like waves in one experiment and like particles in another. Light could be counted as photons, yet also diffracted like ripples on water. Classical physics demanded consistency. Something was either a particle or a wave, either localized or spread out, either continuous or discrete. But quantum phenomena seemed to refuse such clarity. They presented themselves as both and neither, shifting identity depending on how they were measured. It was in response to this dilemma that Bohr introduced complementarity, a principle that would not only shape quantum mechanics, but also alter the philosophy of science itself. Bohr's principle, first articulated clearly in 1927, declared that certain descriptions of nature, though mutually exclusive, are both necessary for a full account of reality. The electron could be described as a particle or as a wave, but not simultaneously. Each description was valid only within the context of a particular experimental arrangement. The exclusivity of these descriptions did not reflect a failure of knowledge, but a fundamental feature of reality. To Bohr, complementarity was not a stopgap but a deep truth. The atomic world could only be understood through pairs of opposing concepts that complemented one another. This was not a matter of subjective confusion, but of objective reality. The act of observation itself determined which aspect of the system could be seen. The principle was controversial because it demanded a new humility from science. For centuries, physics had aimed at producing a unified, consistent picture of the world, one in which contradictions were ironed out and uncertainties eliminated. Complementarity suggested that such unity might be impossible, that at the deepest level, nature would reveal itself only in fragments. For many, this was unsettling, yet for Bohr, steeped in the Danish philosophical tradition of paradox and ambiguity, it was liberating. He saw in complementarity a profound lesson that human understanding must adapt to nature, not force nature to conform to human categories. The famous double-slit experiment became the quintessential illustration of complementarity. When electrons or photons passed through two slits, they produced an interference pattern, evidence of wave-like behavior. But when detectors were placed to determine which slit the particle went through, the interference disappeared, and the system behaved like particles. The two pictures could never be observed together. The experimental setup determined the outcome. Bohr argued that both aspects were necessary for a complete account, but they were complementary rather than simultaneous. Nature, in this sense, did not offer a single image but a dual one, accessible only through different modes of inquiry. The debates with Einstein gave complementarity its most dramatic stage. Einstein, dissatisfied with the probabilistic and paradoxical character of quantum mechanics, devised thought experiments to expose its weaknesses. Could one not, by clever design, measure both the particle and the wave properties of an electron? Could hidden variables restore determinism? Each time, Bohr responded with calm precision, showing how the proposed experiments did not undermine, but instead reinforced the logic of complementarity. The two men clashed in a series of legendary exchanges, Einstein driven by the conviction that reality must be consistent, Bohr guided by the belief that reality at the atomic scale was richer than classical consistency could capture. These debates were never fully resolved, but history sided with Bohr. Complementarity became the cornerstone of what came to be called the Copenhagen interpretation of quantum mechanics, the dominant framework of the 20th century. The significance of complementarity extended beyond physics. Bohr himself often suggested that the principle might apply to other domains of human experience. In psychology, for example, one could view human behavior in terms of subjective experience or in terms of objective measurement, but never fully in both at once. In biology, the organism could be seen as a mechanical system or as a living whole, depending on the perspective. In ethics and philosophy, opposing concepts often coexisted, not as contradictions to be eliminated, but as complements to one another. Though many resisted these extrapolations, they revealed the breadth of Bohr's vision. For him, complementarity was not merely a technical solution, but a profound insight into the limits and possibilities of knowledge. At the Copenhagen Institute, Bohr cultivated complementarity as both a scientific tool and a way of thinking. Discussions with his students often circled around paradoxes, not with the aim of resolving them, but of learning to live with them. His slow, deliberate speech, his habit of pausing and reformulating, reflected this approach. He wanted his students to grasp that clarity did not always mean simplicity, that sometimes the clearest truth was that reality offered no single picture. Many found his explanations elusive, but those who stayed long enough discovered that his patience and openness were themselves a lesson in complementarity. Opposites held together, uncertainty embraced, truth seen as multifaceted. The principle also carried moral weight. Bohr believed that the humility demanded by complementarity was not confined to science but extended to human affairs. In a world increasingly divided by ideology and conflict, he argued that complementarity could serve as a model for dialogue, for recognizing the validity of opposing perspectives without forcing them into premature resolution. Later in life, when nuclear weapons threatened humanity, Bohr urged international cooperation, guided by the same spirit of complementarity. Nations must see one another not as enemies, but as complementary parts of a shared world. Today, complementarity remains one of the most profound and puzzling aspects of quantum mechanics. While later developments such as quantum field theory and quantum information have reframed some of its details, the central lesson endures: the act of measurement shapes reality, and no single description can capture the whole. For students, it is often the most difficult idea to accept, for it runs against everyday intuition. Yet it is also the most liberating, opening the door to a vision of science that embraces ambiguity rather than fearing it. Niels Bohr's principle of complementarity was not simply a scientific innovation, but a philosophical revolution. It taught humanity that reality is not always simple, that truth may come in opposing pairs, and that understanding requires humility before nature's paradoxes. It gave quantum mechanics its philosophical depth and gave science a reminder of its limits. More than a century later, complementarity remains a beacon, not only in physics but in the broader human quest for knowledge. It is a testament to Bohr's unique genius, his ability to see beyond equations into the very structure of thought, and to remind us that the universe is not only stranger than we imagine, but stranger than we can imagine. When one speaks of Niels Bohr, it is natural to think first of his contributions to atomic theory and quantum mechanics, but his true legacy cannot be measured by equations alone. It lies just as much in the people he inspired, the minds he shaped, and the environment of creativity and collaboration he cultivated. Bohr was not merely a scientist working in isolation. He was a mentor who turned Copenhagen into the beating heart of modern physics and helped nurture a generation of physicists who would carry quantum mechanics into every corner of the 20th century. His institute was more than a building, it was a living community of ideas, a place where the world's brightest minds gathered to think, argue, and learn under his guidance. In 1921, with the support of the Carlsberg Foundation, Bohr established the Institute for Theoretical Physics in Copenhagen. At first glance, the institute was modest, a relatively small space by modern standards. But within its walls, a revolution unfolded. Bohr envisioned the institute not as a fortress of authority, but as a workshop of ideas. He welcomed young physicists from across Europe and beyond, creating a cosmopolitan environment where national boundaries dissolved in the pursuit of knowledge. His vision of science was international, cooperative, and dialogical, and the institute reflected this ethos. It became the central hub of what came to be called the Copenhagen spirit, a blend of rigorous mathematics, philosophical reflection, and open discussion. Bohr's style as a mentor was unlike that of many other great scientists. He did not dictate or impose. Instead, he questioned, encouraged, and gently guided. His manner of speaking was famously slow and tentative, filled with pauses, as though he was weighing every word. To some, this was frustrating, but to his students it became a lesson in patience and precision. He wanted them to wrestle with concepts deeply, to consider every angle, to live with uncertainty until clarity emerged. Bohr did not simply hand down answers, he created a space in which answers could grow. Among his students and collaborators were some of the most important figures in 20th century physics. Werner Heisenberg, who formulated the uncertainty principle, spent formative years in Copenhagen under Bohr's mentorship. Wolfgang Pauli, the sharp and critical theorist, engaged in endless debates with him. Paul Dirac, whose work on quantum mechanics and relativity would win him a Nobel Prize, also passed through the institute. Even visiting scientists who stayed for only a short time, such as Albert Einstein, left marked by the discussions they had with Bohr. The list of names is a who's who of physics: Heisenberg, Pauli, Dirac, Landau, Rosenfeld, and many others. Each carried away not only the knowledge of quantum mechanics, but also the unique spirit of inquiry that Bohr cultivated. What made Bohr such an extraordinary mentor was his ability to treat students as equals in the search for truth. He did not patronize or lecture, he entered into dialogue. The discussions at Copenhagen were famous for their intensity. Questions were pursued late into the night. Chalkboards filled with equations, voices raised in excitement or disagreement, but always with the underlying respect that Bohr demanded. He believed that science progressed through dialogue, through the clash and reconciliation of ideas. His role was often that of a moderator, encouraging the young to challenge the old, ensuring that no perspective was dismissed too quickly. Bohr's influence also extended to the philosophy of science. He taught his students not only how to calculate, but how to think about the meaning of their calculations. The principle of complementarity, his most famous philosophical contribution, became not just a scientific idea, but a method of reflection. He encouraged students to embrace ambiguity, to recognize the limits of knowledge, and to see scientific inquiry as part of a larger human quest for understanding. This broadened perspective distinguished the Copenhagen school from other centers of physics, where technical skill was emphasized but deeper questions of meaning were often neglected. The impact of Bohr's mentorship was not confined to Europe. During the turbulent years leading up to World War II, the Copenhagen Institute became a refuge for scientists fleeing political oppression, particularly those escaping Nazi Germany. Bohr welcomed them warmly, offering not only a place to work but also a community of support. In this way, he helped preserve the continuity of scientific progress at a time when the world threatened to tear itself apart. Later, after the war, he extended this spirit of hospitality to young scientists from around the globe, helping to spread the influence of quantum mechanics far beyond Denmark. Bohr's mentoring extended beyond the laboratory to the realm of personal example. His openness, humility, and humanity left as strong an impression as his scientific brilliance. He was known for his generosity, for the way he credited others, even when he had played a central role in their discoveries. He cultivated an atmosphere where collaboration was more important than competition, and where the advancement of knowledge was shared among all participants. Many of his students remarked later in life that what they had learned from Bohr was not only physics, but also a way of being a scientist, a way that combined rigor with modesty, brilliance with kindness. The Copenhagen Institute became, in effect, a school of thought. The Copenhagen interpretation of quantum mechanics was not the work of Bohr alone, but of the collective discussions that took place there, discussions he guided and shaped. This interpretation dominated physics for decades, shaping textbooks, experiments, and the philosophical assumptions of entire generations. Without Bohr's mentoring and the community he created, quantum mechanics might have splintered into competing schools, but under his influence it achieved coherence and continuity. As the years passed, Bohr's role as a mentor only deepened. Even as his own groundbreaking discoveries became part of the past, his institute continued to thrive as a center of innovation. Young scientists still flocked to Copenhagen, eager to learn not just physics but the spirit of inquiry that Bohr embodied. His influence extended indirectly through his students, who themselves became mentors, spreading the Copenhagen spirit to universities and laboratories around the world. The lineage of Bohr's mentorship thus extended across continents and decades, shaping the very fabric of modern science. When one considers the legacy of Niels Bohr, it is tempting to focus on the Nobel Prize he received, the model of the atom that bears his name, or the principle of complementarity that reshaped philosophy. Yet perhaps his greatest legacy is more subtle. It lies in the countless scientists who passed through his institute, in the way they thought, in the way they taught, in the way they carried forward the torch of knowledge. Bohr did not just change physics, he changed physicists. He showed them how to work together, how to respect paradox, how to think deeply, and how to remain humble before the mysteries of nature. In the end, the story of Bohr as a mentor is the story of a man who saw science not as a solitary achievement, but as a collective journey. He believed that knowledge was built in community, through dialogue, through the meeting of minds across cultures and generations. That belief, embodied in the life of his institute, ensured that his influence would continue long after his own discoveries had been absorbed into the foundations of physics. The community he built became the true vessel of his legacy, carrying his spirit of inquiry into the future. When history reflects on the life of Niels Bohr, it does so not only through the lens of his scientific achievements, but also through the recognition he received from his peers and the lasting influence he left on the world. Bohr was a man whose work transcended national borders, whose ideas shaped the destiny of science, and whose legacy continues to echo in laboratories, classrooms, and philosophical debates around the globe. From the moment his atomic model captured the imagination of the scientific community, Bohr was acknowledged as one of the defining figures of modern physics, but the scope of his recognition extended far beyond the Nobel Prize and into the realm of global influence. In 1922, just 9 years after publishing his revolutionary model of the atom, Bohr was awarded the Nobel Prize in Physics. This early recognition confirmed his place among the giants of science and gave international weight to his ideas. The Nobel lecture he delivered emphasized not only the structure of atoms, but also the deeper meaning of theory in science. For Bohr, the prize was not an end but a beginning, a platform from which he could build broader collaborations and encourage open exchange across borders. His Nobel Prize was celebrated not only in Denmark but across Europe, symbolizing the dawn of a new era in physics. The honors did not stop there. Bohr received medals, honorary degrees, and memberships in scientific academies around the world. He was invited to speak at the most prestigious conferences and to advise governments on matters of science and policy. Yet what set him apart was his ability to use these accolades not for personal prestige, but to promote international cooperation in science. He saw recognition not as a trophy but as a responsibility, a tool to encourage dialogue and to build bridges between nations. In this way, his reputation became not only a reflection of his discoveries, but a force that shaped the scientific community itself. Bohr's impact was perhaps most visible in the debates that shaped quantum mechanics. His principle of complementarity, his defense of uncertainty, and his philosophical reflections gave quantum theory its intellectual backbone. For decades, his interpretation dominated textbooks and classrooms, forming the foundation on which countless experiments were built. Even those who disagreed with him, like Einstein, helped amplify his influence by engaging in debates that became legendary. In this sense, global recognition of Bohr was not simply a matter of awards but of influence. His ideas defined the conversation, and his institute in Copenhagen became the epicenter of a worldwide revolution in science. Beyond the academy, Bohr's recognition took on a political and moral dimension. During the Second World War, when Denmark was occupied by Nazi Germany, Bohr's Jewish heritage through his mother placed him in danger. He fled to Sweden and eventually to the United States, where he contributed to the Manhattan Project, though his role was more advisory than technical. Yet even in this context, Bohr's reputation carried weight. He used his influence to advocate for openness between allies and later for international control of nuclear weapons. After the war, he traveled widely, meeting with leaders and urging cooperation rather than competition in the nuclear age. His open letter to the United Nations in 1950 called for global dialogue and transparency, reflecting his belief that scientific knowledge, like complementarity, demanded collaboration between opposing sides. This political dimension of his recognition ensured that his legacy extended beyond physics into the ethical responsibilities of science. Bohr's global influence also rested on the network of students and collaborators he nurtured. Through his mentorship at the Copenhagen Institute, He helped train a generation of physicists who went on to shape science across continents. These students carried his ideas, his style of thinking, and his spirit of collaboration into universities and research centers around the world. In this way, Bohr's recognition was amplified, not as a single figure celebrated in isolation, but as the leader of a community that spread his influence far beyond Denmark. His name became synonymous with the Copenhagen spirit, and his institute a symbol of international scientific exchange. The recognition Bohr received from his own country reflected the depth of his impact. In Denmark, he was celebrated as a national hero, not only for his scientific discoveries, but for his role as a moral leader. The Carlsberg Foundation provided him with an honorary residence next to the brewery, a unique gesture that symbolized both respect and gratitude. His image appeared on Danish currency, and his memory is preserved in institutions, museums, and foundations dedicated to continuing his vision of science and society. To the Danish people, Bohr was not just a scientist but a symbol of intellectual achievement and moral responsibility. Internationally, Bohr's legacy has only grown stronger with time. His ideas about complementarity continue to influence not only physics but also philosophy, psychology, and even discussions of international relations. The debates he engaged in with Einstein remain central to the teaching of quantum mechanics, illustrating the profound questions that still inspire students today. Modern fields such as quantum information theory and quantum computing trace their conceptual roots to the framework Bohr helped establish. In this sense, his impact is not only historical but ongoing, woven into the very technologies that shaped the 21st century. The honors that came after his death in 1962 testify to the depth of his influence. Institutions across the world bear his name, from research centers to awards that honor excellence in physics. His writings continue to be studied, his ideas debated, and his role in the birth of quantum mechanics retold in countless histories of science. More than half a century later, Bohr remains a touchstone for discussions about the meaning of science, the responsibilities of scientists, and the relationship between knowledge and society. What makes Bohr's recognition remarkable is the way it combined the scientific, the philosophical, and the moral. Few scientists have managed to shape equations and ethics, laboratories and politics, philosophy and technology with equal force. Bohr's recognition was not confined to medals or ceremonies. It lived in the way people looked to him for wisdom, guidance, and inspiration. He embodied the idea that science is not only about understanding the natural world, but about shaping the human one. In the final analysis, Niels Bohr's global recognition and lasting impact rest on a combination of brilliance, humility, and vision. His discoveries changed physics forever, his mentorship built a generation of leaders, his philosophy reshaped our understanding of reality, and his advocacy sought to guide humanity through its most dangerous scientific advances. The honors he received, the institutions that bear his name, and the continued relevance of his ideas are all reflections of this extraordinary legacy. More than a century after his birth, Bohr remains not only the father of quantum theory, but a father figure for modern science itself, a reminder that the pursuit of knowledge is both a privilege and a responsibility.